So on Monday, we went over just the basic intuition behind convolutional neural networks, but we also discussed quite a bit in quite a bit detail about what artificial neural networks are, because artificial neural networks are still part of the convolutional neural networks. Before we get to that stage of the artificial neural networks or deep neural networks, we have to perform several operations on images before we put that the processed image as an input to the artificial neural network. The ideas behind basically, the object identification or classification is still done using artificial neural network, but just because we have the data in the form of images this time, we will have to do some other operations. Okay, so the reason why it's called convolutional neural network, because there are several convolution operations that are done on images before the image is transformed into the input to the deep neural network. Okay, so we're going to go over just the intuition behind what a convolution operation is, what it does, and then what is pooling, what is flattening, then finally getting to the flatten full connection part before we actually code that in a Python framework to just get the results. So what we very briefly said on Monday was that as humans, we see things like that, right? All the way on the left. We see, some humans with faces and chairs, tables, all these different sorts of, objects within the, the perception that we have, like the environment that we perceive, okay? How we do that? Based on, quite a few features, okay? So basically characteristics of some objects, and we extract some features, and based on those features, then we make a decision that what we are seeing in an image is some sort of object, something like that, okay? So, but what the difference between the computer and the human is that we see things like that, those objects, but what the computer sees is just a bunch of pixels, okay? An image with it just a bunch of pixels, either in one channel, like if it's a grayscale channel, it's just one channel, one 2D image, or if it is a 2D, if it is a red, green, blue image, we have a 3 dimension, okay? Like 3 dimensions, red, green, blue channel of 2D pixels, just a bunch of pixels. And then the operations behind those are just simply done using some sort of distance calculation or differences between the. So there is still some arithmetic operations that are actually going on behind the actual intuition of the convolutional neural networks or even image processing. So we will talk about how computer looks at this, takes this as an input, and basically identifies objects based on the pixel values, based on the value of every single pixel within the image, even within different channels, okay? So how does it do it? Robert. System. Mm-hmm. So when it's Boolean, you really don't have to do any other transformation. You already have the gradient, full gradient, like full 100% gradient from this pixel to this pixel, this pixel to this pixel, and this pixel to this pixel, because this is the maximum change that you can see. So you will still see the full gradient in its fullest form, in its pure form, when you just have only zeros and ones. Images are not usually zeros and ones. No, it does. So we do actually look at a red, green, blue channel. So these channels are actually combined together using some technique that these 3 channels are combined together and just one image is created where you can see the combination of red, green, and blue values. So in that case, every pixel in red, green, blue, every pixel has a value from 0 to 255, between 0 and 255. And then, as I said, every channel, every pixel has red value from 0 to 255, green value from 0 to 255, and blue value from 0 to 255. They're combined together and a color can be seen. This is what our human eyes basically can see in red, green, blue channel. in reality, in actuality, there are many more color spectrums that human eyes basically cannot process. Okay, what we can see is in just red, green, blue channels. Okay, there are multiple other ranges of colors that human eyes basically are not able to process. Just like how we cannot see infrared, how we cannot see, multiple frequencies through which our phones connect, right? These are different wavelengths that our eyes basically are not designed to process. Yeah. So just like a very simple example. Suppose that you are in a room with no window, no door, nothing is completely closed. Hope you are not in that, never in that room though, by the way. You're in that room where there is no light. There is no possibility of light entering in that room, okay? You will see, darkness everywhere. If we put an infrared, device in there that actually projects the light in an infrared spectrum, you will still see everything else dark. But if you basically put, a bat, I don't know which bird is the one that actually can see infrared spectrum. The bird will actually see everything bright because they are able to process infrared spectrum with their eyes while humans can't. We will still see everything else dark. Okay, just like, I don't know if you've ever tried this very childish experiment, is that when you hold the remote control of your TV or anything, and then you just like put it in your eye and you just don't see anything. If you put a camera and video, and you will see the light basically blinking. That's infrared. Okay, infrared, and you are not able to see through your eyes. What I'm saying in here is that the computer basically sees what we perceive as just a bunch of pixels. And then there should be some operations that should be performed before we get to the artificial neural network in order to do some classification, some identification, and anything that needs to be, detected within the image. Ronnie. There is a huge spectrum of, light wavelengths that can be seen by different species, different, animals, and humans can only see the light spectrum, a specific range of wavelengths, which we can see in process. Anything that is above or below that range of wavelength, we will not be able to see. So it's ultraviolet is actually one of that. Then infrared, it's just with different wavelengths. Okay, it's a whole spectrum. Okay. Say that again. Well, with infrared, it's like body. I just gave an example. Some other, species might be able to see the infrared or maybe another wavelength. What I was saying that as humans, we can only see just within specific range. All right. First thing the convolutional neural network starts with is it takes an image, all right, and applies several convolution operations. What is it? How many of you have heard or actually performed convolution operations? Yes. Okay. So what we do is a convolution basically is a very, very simple operation. What we do is in the convolution operation, we take a smaller filter. Remember in one of the week 1 slides where I showed that the convolution operation, we basically run a small portion of a combination of pixels, and then we simply run that small filter over the image in order to find specific types of features. Okay, so the convolution operation, what it does is you have an image on the left side, you take a filter, a specific filter, you convolute it, simply convolute it. What do I even mean by convoluted? Convolution. Convolution is simply a dot product. This is a dot product. Dot product. This probably might look very scary to you, but it's just simply what it's doing is, let me show you what it does. So we take a bunch of filters to identify, find different edges or different features within the image. An image may have horizontal edges, it may have vertical edges, it may have diagonal edges, it may have more complicated, complex features or complex combinations of edges. Like for the chair, I am seeing mostly like, linear edges, right? For a chair, if I look at it from a distance, it's just mostly linear edges, right? So that means if we are to detect a chair in an image, we will have to find the horizontal and vertical edges, mostly, right? Or a roof, right? So a table, a desk. So we'll have to find basically vertical, horizontal edges. And how do we do that? We basically put, different values of filters. Now you see if there are ones in the vertical direction, then that means we are looking for vertical edges. If they are in a form like this, if a filter is like this, 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, then that means we're looking for horizontal edges. So what we do see here is at convolution operation, if you look at this equation, all what it's doing is it convolutes this filter on top of it. So it will place, first time it will place, this filter will be placed right here, a 3 by 3, and it will just do a dot product. What do I mean by dot product? Like 7 times 1 plus 2 times 0 plus 3 times minus 1 plus 4 times 1 plus 5 times 0, and so on and so forth. And then at the end, it will just do the sum. It will do an element-wise product and then calculate this. That is all what convolution operation is. Okay. So what convolution is used for is to find out different edges in different directions, edges of different shapes within the image. Because this is what the convolutional neural network needs to learn. What sort of edges am I looking for within the image? And it is basically a combination, a collection of multiple different types of filters that we can run on the image and then find out different edges. Once we do find out the different edges, we actually train filters. So these are the filters. These are the small filters that we apply on an image. And then the resulting part basically becomes not only just, edges, more prominent edges within the image, but also of the smaller size. You see the image is getting smaller in size, but we're still preserving the edge information within the image, right? So you see here, I run 3 by 3 on that 5 by 5 matrix, right? And at the end, I'm getting 3 by 3 matrix. Pretty good, right? So you see where did this 6 come from? It ran the first convolution, this operation, it will just show here. And the result basically was 6. And we put 6. And then we move that filter just 1 pixel ahead, then 1 pixel. It is up to you as a developer, how many pixels do you want to move that convolution filter over? Just 1 pixel, 2 pixels, multiple pixels. So it's up to you it's up to the problem that you're solving. Do you really need to just move one pixel or more pixels? Okay. So you apply convolution and then basically get a smaller, matrix, but still preserving that edge information. But one thing you will notice that we have values in minus, right? And I said red, green, blue channels are only from 0 to 255. How can we convert this into a matrix where the minimum value is 0? Only minimum value is 0, but we will still preserve the edge information. How do we do that? Rectifier linear unit, rectifier function that we apply. Remember the equation behind that was we just simply choose the maximum between x and 0. Between x is the actual current pixel value and 0. If x is less than 0, then obviously you will select 0. With that, all the minus values, all the less than 0 values will be converted to 0. Sounds good? So this is all what convolution does. The G is the small filter. It basically is run over the F, which is the image that you have, and we have a smaller distribution. A smaller distribution, but we still preserve the shape of the distribution using just this formula. So we apply convolution on an image because we want to know what sort of edges that we have, okay? And what we do then is we apply convolution and then we run several filters, not only just one, because our image might not only have one type of edges, right? It may have horizontal edges, it may have vertical edges. It may have circular edges. It may have like elliptical, like ellipse type edges. It may have a combination of all of those, right? So we apply multiple filters on an image at each layer, and we perform the convolution. And then we combine all of them together and flatten the layer. And after that, the image basically gets converted into a vector of specific values. And then those values, that sequence of pixel values, get learned by the convolutional neural network, and it memorizes that kind of pattern and says, every time when I see a pattern like this in an image, I will be trained, and I will decide that it's kind of a specific shape within the image. So not only just horizontal or vertical, I mean, like Ronald's head looks more round to me, right? So it's a circular. If I'm looking for the wheels of the car in an image, I will apply a circular filter, right? Something like this. In that case, I will have, let's say if I am applying 5x5 filter. So I will have 1, 1, 1, 1, 1, 1, 1, 1, and the rest 0, 0. So that becomes like a circular filter, right? So we combine multiple filters together. We apply that on the same image. We reduce the size of the image, because if we don't reduce the size of the image, just imagine how large the vector will be before it goes to the actual deep neural network. So we have to still reduce the size while we do the convolution operations, reduce the size of the image, but still preserve all those edges using these convolution and rectifier operation. Sounds good? Ronald. Preserve all the edges. Yeah, edges within the image. So you apply convolution. Suppose that the only way that you apply to reduce the size of the image is simply drop some columns and rows, then you're losing a lot of information. You might lose a lot of information about the edges within the image. We don't want to do that. We want to apply some operation so that we still preserve the information about the images, even if the size of the image gets reduced. You're zipping a file, you're reducing the size of the image, but you're still applying a clever operation to find all possible edges within the image using that dot product. So it's a compression plus. Sorry? We construct what, sorry? No, so the image gets reconstructed with the edges within the image. Okay, so it's a compression. It actually compresses the image, but before it compresses the image, it finds out all the edges within the image. Okay, all right. So then I say that convolution actually reduces the size of the image, but it doesn't reduce, as fast as without the pooling operation. Okay, the pooling operation is done after the convolution so that we can reduce the size of the image much faster. And what do we do in the pooling operation? There are 3 very common pooling operations that are performed on the image or on the transformed image. Right after the convolution and rectifier linear unit operation, we take the image and we simply run again a small, not filter, like a small size, and we find either the maximum value of that region or the minimum value of that region or the average. And we simply pick that and we put that into the pixel. Something like this. You see, first time the blue area started, right? We actually moved this region, had this region, found out that this is, so okay, by the way, minimum, maximum pooling, and average pooling. These are the 3 most common pooling operations that are done in convolutional neural networks. The most famous is maximum pooling, max pooling, because max pooling actually preserves the edges, the gradient between different pixels more strongly compared to minimum and average. But there is no specific reason behind always using maximum pooling. Okay, it depends on what type of, once again, what type of object you're trying to identify within the image. Max pooling it preserves basically the edge information or the intensity of the change, the gradient information better. All of them do that, but minimum and average preserve the less intensity of the gradient as compared to maximum pooling. So maximum pooling is actually the most famous pooling operation that is performed in convolutional neural networks. All what we do is we actually find a kernel. Basically, we say how many pixels we have to look the maximum from, like a kernel size. Basically, here you're seeing 2 by 2, right? A 2 by 2 kernel. And then from 2 by 2, you find the maximum and you put that into a new image format. So in the first one, we found 5 as the maximum, right? Out of all those 4 pixels. Then what we do is we move this kernel next, and we find 7 as maximum. And we put, no, not 7, sorry, 9 as maximum. How do we decide that how many pixels we have to move? It's basically using a stride. Stride of 2 means I'm moving 2 pixels over. 2 pixels over, because I really don't want to include the pixels, the column that was already included, right? Okay, kernel size and stride. That's what we will have to remember. So we do the max pooling. Now you see in 4 by 4 matrix, we have just converted it into 2 by 2. Okay, so we do the, Nathan. What if the window is, colors are,
first column was red.
okay, if the first column was red, this one?
In every example here where you're playing the color is the same for each, right? What if the colors are mixed?
No, the colors are different. I mean, there is blue, green, yellow, and red. Is this what you mean? That's measure. We're finding out the maximum from each of the kernel.
Right. I realize it's iterated 4 times.
Mhm.
Each time it's iterated.
Oh, no. The colors. So here, the color doesn't have any meaning. All what I'm saying is that I'm moving the kernel, in that square first, and then I'm moving it to the next square, and then I'm moving it to the next square and next square, just 4 times. So these colors only represent actually the location of the kernel that we're moving. Yeah. There's no meaning behind the colors here. It's all what it represents is actually the location of the kernel that I moved. Okay, yes, strike. How many pixels you move? No. 2 pixels in from left to right, horizontally. So when you get to this part, and then it goes down 2 pixels, strike down 2 pixels, and then it starts from there. Okay. All right, from left to right, then two pixels down from left to right, then 2 pixels down from left to right, all the way down in the image. Okay. Sometimes, now suppose that if the stride goes all the way at the end of the image, but we don't have a 2 by 2, we just are left with just one pixel. Suppose that if the stride now has to move here, what happens then? Well, the program will throw an error to you. What developers do is actually add a padding layer. It's called padding. Just like this, with zeros. Okay, just a padding. All right, that's great. We apply several convolution and pooling operations, and then we simply flatten the matrix. What do I mean by flatten the matrix? Suppose that at the end, I am left with 1, 2, 3, 4, 5, 6, 7, 8, 9. All what I will do is I will flatten it. Just like that. I flatten it because that's how the artificial neural network takes input as a vector, And then I just train the neural network with different layers, different hidden layers.
So
Yeah,
finding it means splitting it.
Yes. Not training it, transforming it, just. Okay, all right. We flatten it into a vector, into an array, and then we simply just train our fully connected layers, the deep neural network that we had, just like this. So you see, we provide the convolutional neural network an image as an input. We apply several convolution operations using multiple different filters at each layer. We do the pooling to reduce the size. We again do some convolution operations, do the pooling, reduce the size. We keep reducing the size to a certain point that where our machine is able to then, convert the larger, basically, filters into an array. And then we simply finally provide it to the deep neural network that we have. Sounds good? It may not be just deep. When I say deep neural network, when there are multiple hidden layers for more complicated problems. So majority of the real world, neural networks that are designed to do object identification, classification, they're using deep neural networks because they're for multi-class classification. What we're going to cover today is just only one layer of neurons, and it will be called feed forward or shallow. But the thing is, before the image gets passed to the deep neural network, it goes through several operations. Make sense? And then finally, with the output, we apply either some of the activation functions, and then we basically get, if we are applying softmax or sigmoid, we're just getting a probabilistic classification, right? It says that these neurons say that if I am seeing a specific pattern in this fully connected layer, flattened layer, then maybe it is a zebra. 70% that chance that it is zebra. So this is actually the actual format. Let me just go over this to show you an interactive demo. Can I click it? Nope. Come on. All right, I'll have to open it from outside the PowerPoint. That's how I know to open it. And you gotta be kidding me. Why don't I have permission to open the model? That's weird. Yep. So the guy who developed this model basically has forbid the access. Wow, how unfortunate. But basically, this is a web demo that, actually, you know what? Let me just try to look for it online. How to develop? Nope, and a demo. Let's see if I have that. So there's this more simpler version of the same network, but it doesn't show the actual convolution operation. So what I would do is, if I say clear, and I say, let's say, draw 2 and read, not so good. It's reading as 8, which is really bad. Maybe 7 again. Your number is 7. But I wish that this other model was there. I think TensorFlow. I saw a TensorFlow. All right. Handwritten digit recognition. if you see a demo anywhere, probably not. Not in Code Lab. Oh, I had it yesterday, but I don't know why it says it's forbidden now. So that's not great. I wanted to show you the demo. Where is the demo? Sorry? Oh yeah? Okay. TensorFlow, TensorFlow. Oh, it was a very interactive demo. I wish it was. Or I don't know if they show it on YouTube. No, that just opened up the TensorFlow website instead of. Anyway, it's okay. I actually have a few other. So what it will show is that, you know, if you draw something right here, it will actually show you the convolution operations, you know, multiple filters that are trained on the image, multiple convolution operations to find out different types of edges, then the cooling operation, then another convolution layer, then cooling, and then finally look the flattening layer. And then finally it is provided as an input to the deep convolution deep neural network. And if you draw anything, it will basically take the output and it will show you that my first guess is that this number is 4. My second guess is that this number is 1 or 7 or something like that. So it actually was a very nice interactive demo that that actually show you the operations of these convolution and cooling, etc. Okay. I have the website that shows online models. Oh, you did? Okay. It does? So that means he has probably restricted my access only, that guy. I don't know. Oh, it's a different. Okay, it's a different website. It's a different person. All right. So let me show you this. I think it's a very cool interactive demo that what is that? So let's say which just propose a digit. 8. Oh, wow. Not good at all. But you see, still, its first guess it was 8. Where does it say first guess is 8, second guess is 6, right? So you see here, let me show you. This was the actual image, pixels, right? If I move my cursor over to one of the pixels there, it actually is convoluted from this bunch of pixels. So it shows the live demo that this pixel came actually from this bunch of pixels by applying the convolution operation on this one. Okay, and then we have max pooling. So this max pooling was done from this 2x2 kernel. And then we have further convolution operations. You see? All right. So the convolution operation is done on these train filters and then max pooling. And then finally we have the flattened layer. And then it's provided to the deep convolutional neural network. And then at the end, it just does the classification. So that means the classification in this part is actually the 10 output neurons, right? 10 output. 1 for 0, 1 for 1, 1 for digit 2, and so on and so forth. So 10 nodes that are actually predicting what digit it might be. It's actually a pretty cool demo. There is a bunch of other TensorFlow models. If I say, let's just go with the body segmentation, we'll have to look for a demo. How to run it? No, I don't want to run it. I just want to run a demo online. Folder, demo, where is demo? There's a demos folder. I think I just actually checked it last night. Why don't I just do Control F and demo? Sample code, demo folder, shared. It will live Canva demo. Let's see. Is it doing anything? Oh, it's an upload. How to run a demo? All right. Wow. Okay. So we're using media pipeline segmentation. Is it getting the frames? Run? No, this is for the video file, I think. Nope. Wow. Live demos. Never go as expected. Not upload a video. How to run a demo. All right. I'll have to just go with another model probably. Oh, it is there. So how do I close? I want to close these controls. Close control, and if I stand back, I don't know if it will do any segmentation because it's just way too large, the image. Maybe if I open the controls and have the camera, maybe 360. Will I try to do the segmentation? No, it's not working properly. Let me show you another pose detection. There was one more that was a face landmark. You code, and it also had a demo. What if I bring this? Oh. So you see, this is one of the most interesting model that someone has developed. It's because, using these facial landmarks, you can actually identify the impression that someone is making. So it can be a good model for like deception detection, lie detection at border, control, for border control. It can be, used to identify basically, different impressions from different people at multiple places. Or it can even do, you can basically find all these facial landmarks, have someone else sit and record the video and put your face on it. That's what deepfake does, right? So this is one of the most interesting because I think it identifies 100 and something more than 100 facial landmarks that are very useful for video processing purpose. So this is one of the most interesting models that someone has come up with. Pretty interesting. There is another that you can see as I'm going to close this. You may have simple face detection. Just like, from a video, you can detect the face and then use different filters on your face. Like different makeup, or you want to see how do you look like with long beard or with different hairstyle. So you can detect a face. How do I those controls? I don't know. Yeah, it detects with basically my nose, my eyes, ears, and my lips. So it actually, the other facial landmark detection, it detects all the landmarks, all the changes on the face, like jawline, like, lips, nose, eyebrows, eyelashes, eyes, everything it can detect very, with a very high accuracy. So this is something, I would really suggest if you can go over just these, open source models, by the way. These are open source. You can download the models that were trained on specific data sets, and you can use those trained models to perform your own classification on something completely different. This is what we're going to do on Monday. We're going to use a pre-trained model for something else that was designed for completely something else. We are going to use our own data set to design it on a totally different, problem. What are the ways? Well, the ways are to just simply change the structure of the artificial neural network or the convolutional neural network. You may want to include more convolutional layers, or you may want to reduce the convolutional layers to identify. This is actually one of the painful issues with neural networks, that it's a black box model. It is not very easy to find out the most appropriate structure to solve a specific problem. I mean, TensorBoard, like TensorFlow has done TensorBoard, developed TensorBoard as a JavaScript library to find out what it might be, or to tune the model. It's still not very, intuitive, very transparent. This is one of the problems, one of the issues with neural networks, that, no matter whichever design you come up with, you cannot be 100% sure that this is the best structure that you have designed for a specific problem. But you can always do that by basically trying different, different structures, different number of layers. This is what we're going to do today in the coding example right now, in just a few moments. Okay. So some of these are very interesting. You can download, these open source models and apply them for completely your own purpose. So what we are going to do is we're gonna perform classification on this problem. Let me just close this. No. I'll just. We'll do a cat or dog classification, image classification. So we will actually write our own convolutional neural network. Remember, convolution, pooling, multiple convolution pooling operations. Then we're going to flatten our images, our filters, into a 1D array. Then we will implement our neural network. As I said, we'll just only do one layer, right? One layer. And then we're just going to do the binary classification, right? Because all what we're detecting from the image is if there is a cat or a dog, if any of this is detected. And why do we have just only one node? Because binary classification can be done. Suppose that if the answer is 1, it's a cat. Otherwise, it's a dog. If the answer is 1, it's a cat. If the answer is 0, it's a dog. So we can just simply do it with one output instead of 2. Okay. So we're gonna basically have a data set that has 8,000 images of cats and dogs, basically divided really nicely. Someone has done, the processing on this data set, basically separating 4,000 images of cats from 4,000 images of dogs. And then we're going to use the test set on which we're going to test our model. Remember, we said that we're going to develop our model. We're going to do the data collection, data pre-processing, model development, and then model evaluation. How good the model is on the data that is completely unseen, right? We have to test it, how good the model is, and then we'll do the model evaluation, right? So we have this data set that has 8,000 images of cats and dogs as training set, and then 2,000 images of cats and dogs as test set. And we will see how good the accuracy is. Once again, this might not be the best structure that we may develop. There might be a better one, but only two convolutional layers can get us up to more than 80% accuracy, which is still not bad. But you can test, other, convolution operations, more convolution layers, or maybe more dense, network to see if the accuracy improves. Okay, so this is what we are going to do. Okay, we're gonna program this. So in about 2 minutes, I'll open my TeamViewer connection to my home computer, and then we're just gonna go ahead and start. In the meantime, if you have any question, please feel free to ask. Otherwise, we're just consider it as a 2-minute break. What do you mean by fragile? No, no. So TensorFlow, the library that we are going to use, actually uses tensors, not the 2D array, not the actual data structure that is array. Tensors are designed and developed by TensorFlow, Google TensorFlow, to handle two-dimensional arrays much better than just a 2D array normal NumPy data structure. And it is designed to basically process those 2D arrays much more faster than the actual data structures, the actual 2D array. So tensors are developed to actually process the data on a GPU, graphics processing unit. So it's a much faster technique, much faster, much better, efficient data structure to work with images. Okay. It's another data structure, I should just say. I will explain that in the next lecture, because we are going to have some discussion on the data types. All right. So, by the way, please remember this slide, because we're going to have to follow this slide. So we're going to use 32 filters. Remember, 32 filters, 3x3 matrix in the convolution operation. Then we're going to have a 2x2 kernel, the pool size in max pooling and with stride of 2, which we just discussed in the slides. Okay. And then we're going to apply another 32 filters, 64 altogether, and then another pooling. And then finally, we're going to combine that together, convert it into a flattened array, and then pass it to our neural network. Sounds good? All right. Cancel. We have the data set, okay, training set, 4,000 images of cats and dogs. Some of them are really cute. And 4,000 images of dogs. So the convolutional neural network is actually going to process each of this image and learn the features. All right. And then we're going to do the evaluation, model evaluation on a test set. So this is the 1,000 images of cats. It's going to do the prediction by never seeing this image in the training process. And then at the end, what we're going to do is just to test that the validation accuracy is above 80%. We're going to test our prediction on these two images and see if the convolutional neural network detects it as a dog or as a cat. Okay. So what I'm going to do is I'm going to open this file and I'm going to start coding. Sounds good? So let me just go over. How can I just have the slide here? What happened? All right. So I'm gonna say, you know, CNN for cat dog classification. All right. So this time, what we're gonna do is we're gonna import the required libraries that we would require. Okay. So the only library that we are going to use for CNN development is just going to be TensorFlow. So TensorFlow is a complete package that can be used to design a complete convolutional neural network. Okay, so we're gonna import basically, you know, TensorFlow in this. I think, is this somebody's phone vibrating? I don't know, or is it just my ears? No. All right. So import TensorFlow as TF. So we're going to use basically TensorFlow to create all the entire convolutional neural network structure. Okay. Basically, that is going to do the convolution operations, pooling operations, flattening operation, and then creating a dense, you know, artificial neural network. Okay. So we're going to use that. On top of TensorFlow, there is another library that is developed, which is Keras. We have already done that. It will basically, we will use Keras for, you know, do the data pre-processing because we have the data set in the form of images this time. So we're going to have to use a different library to do the data pre-processing this time. That the other day we used scikit-learn pre-processing, right? So this time we're going to use keras.preprocessing.image, an image data generator. And I'll tell you why we would need to use a library like that for pre-processing the images so that we have a much more larger data set with different variations so that the convolutional neural network is more robust. Okay, so we're going to use Keras from keras.preprocessing dot image import image data generator. Okay. Sorry. Yeah. Right. Okay. So we're going to use the image data generator. I wish I had the time to go to actually keras.io. Keras.io is the website where the complete documentation of Keras is given. And you can, just like how we went to sklearn that day, right? And then basically copy different functions from there, different libraries from there. You can do the same with keras.io. You can go to keras.io and say, click on image library, and then image data generator will show you the complete documentation of what functions are there, how to process or pre-process the images. Okay, so first, what we need to do is, see, I forgot to show you the slide that we are going to have to follow, which is this one. Okay, we're gonna have to import the libraries, load the data set, do the train test split. We will have to skip this part today because remember, I showed you the folders where the split is already done. We don't need to do anything about that. Then we will have to do a little bit of data pre-processing, and we'll do the model development, and at the end, we'll test the accuracy. Okay, so we will have to remember that. And let's do the, so first, we will load the data set, right? We're going to put it into another. Load. So we'll load both training and test data set, right? So if I just increase the size a little bit, which is going to be easier for all of you to see. Load the data set. So I'm going to use training data set generator, okay, from image data generator. And I'll tell you what the input arguments are. Let me just write them first. 1, 2, 55. So this is basically, remember we said that it's better to basically normalize the data to have it between 0 and 1 range or standardize it. So this time we're going to transform each pixel value from, instead of 0 to 255, to 0 to 1 only. So all the pixel values are going to range from 0 to 1, which is going to be better for the convolutional neural network to process much quickly and much more uniformly. Okay, so this is basically, I'm rescaling each pixel by 1 by 255. I'm dividing each pixel value by 255 so that every single pixel value is going to range between 0 and 1. Sounds good? All right. Then what we can do is, now you see we had images of cats and dogs, right? Like taken. What we want the convolutional neural network to be more smart, to still do the prediction if we were to see the cat or a dog from a different angle, right? Something like this. If I'm looking at you guys like this, I'm just having, you know, a proper view. What if I had to look at you like from a 45 degrees angle, right? Then your shapes are going to be different, right? So we want the convolutional neural network to tell that even if you are looking at it from different angles, you should still be able to predict it, right? So we're now increasing the size of the data set to a much larger data set. We're taking one image, each image from the data set, and we're just simply rotating it in different directions. Okay, rotating it in different angles. All right, that is the argument that is called shear range. Shear range does the, you know, the rotation for you. Okay, we also want the convolutional neural network to do the prediction at different zooms. Suppose if you were looking at the cat from a very close distance or really far, right? So we will also want to do the convolutional neural network, make the convolutional neural network to do the prediction, you know, from a distance too, right? So what we're going to do is we're going to do the zoom range. I will explain what these 0.2 means, but let me try to finish it because we're running out of time. We're just only left with 5 minutes. And then what if you're looking at the cat from the in a mirror? You should still be able to predict. So we're going to do the horizontal flip of the image. We're just showing the convolutional neural network a mirrored version of the same image. All right. So what we are going to do is horizontal underscore flip equals true. Sounds good? So now we have taken those 8,000 images and we have increased the data size from 8,000 to multiple, like tens of thousands of images now, because we have done some augmentation on the images. This is what is very common when you're developing convolutional neural networks. Okay, so that's great. Then I'm actually going to generate the training set. Okay, the training set from, did I name it training gen? Okay, training gen flow from directory where you see I have the folder data set in my folders, right? From the data sets, I am going to use all the images from the training set directory. Okay, from the training set directory, so these images were actually taken using different cameras at different zooms, et cetera, et cetera. So the dimensions of each image is not going to be the same. The dimensions of all the images doesn't match. If the dimensions don't match, then that means the convolution operations and pooling operations are going to mess up completely. So we have to tell the convolutional neural network, or we have to, how I should say, resize the image, resize each of the image to a one size, so that the convolutional neural network should apply the same operation on all different images. Okay, so we have to say we will convert the target size of the image as 64 by 64 pixels. You can do 132 by 132. That's fine. It's just a proposed, you know, dimension of the image. We take one image, we rescale it to 64 by 64, just a square image. Okay, and it will apply on all the images that we have. Okay, we have to do the target size. And there is another argument called bad size. Remember, we were talking about the backpropagation. The research, the literature says that backpropagation using only one data sample is not as good as when you calculate the error on a collection of samples and then propagate back. So there are reasons behind it. Because of the time, I won't be able to explain too much. I will explain it on Monday. But it's better to actually get the training error from a collection of images or collection of data samples, and then backpropagate the error. So all what we were going to say is, instead of each sample, we're going to calculate the error from 32 images and then send back the error. Okay. And then finally, I'm going to say the class mode basically is binary. Sounds good? And I need to do that with the training set too, right? What we will have to do is, because the test set is the set that is never going to be seen by the model, we really do not need to do any transformation on the test set because it's the test set. We really don't need to do any angles or anything on it, right? Okay, so I'm not going to use any of those. And then what I'm going to do is I'm going to call this as test gen. And I'm going to say this is going to be the test set. And I'm going to call the test set. And I'm going to use all the images from my test set grid. That's it. All right. Then there is this really nice, cool library from Keras that we can use, something like this. Keras sits on top of TensorFlow. So tf.keras, and it's called sequential. Sequential is the library that provides you all the operations, convolution operations, and everything. So now we can start implementing the convolution, pooling, and flattening, right? So we can do something like this. CNN.add, right? CNN.add tf.keras.layers, and I'm going to do the convolutional 2D convolution operation. Convolution 2D convolution operation. How many filters did we say? 32, right? What was the kernel size? 3 by 3, right? What is the activation function we're going to use? ReLU, rectifier linear unit. And finally, we need to tell the convolutional neural network what should be the size of the input. 64 by 64, right? So it's called input shape. It should be 64 by 64 and 3 channels. Red, green, blue. 64 by 64 and 3 channels. Okay. Okay. I'm going to run over it quickly, very quickly. And then all what I'm going to do is I'm going to do CNN.add tf.keras.layers, and I'm going to use max pooling this time, right? Max pool 2D. What did we say pool size was? 2, right? And then I said the strides should be 2, right? That's it. We're done with the first layer of convolution and pooling. And I said we were going to implement 2 layers, right? 2 convolution layers and 2 pooling. So I just simply copy this. One thing that I have to remove from this convolution layer is that because the top layer already knows what the shape of the input is, we really don't have to do the shape input because the shape is already coming from the top layer of the convolution. All right, finally, max pooling. And the next layer was actually the add Keras, not the Keras.layers. dot flatten. All what I will do is I'll just flatten my input matrix, right? And finally, after that, remember what was in the slide? Oh boy, we're running out of time. We have run out of time. So we flatten, and then our flatten array, and then we are just simply going to create a dense layer of 102 neurons with ReLU function, activation function, right? So let me just do this, and I'm going to stop, and we will continue developing our convolutional neural network on Monday, okay? So that this gives all of us the incentive to come to the class and not skip the class. Flatten, and then I'm going to do CNN dot add TF dot keras dot layers dot dense, right? And how many units? 128. Sounds good? We're going to do the activation, which is value. And then finally, only one more. I promise just one more now, so that we're done with the implementation of our convolutional neural network. CNN dot add TF dot keras dot layers, another dense layer for the classification, the last output neuron. And this time we are going to use the sigmoid operation to do the probabilistic classification. So we're actually done with the developing, loading the data set, pre-processing it, designing the complete convolutional neural network model, and we are just going to left with compiling and training it on the data set itself. And then finally, we'll do the evaluation and see how good the model is. And we will do that on Monday. I will not upload the code today for this class, because if I provide the code, then you guys won't come on Monday. And I will be really upset. I want all of you guys to come to the class so that we can have